Okay, all right. Welcome to lunch. You're welcome to have lunch. It's a good time to have lunch. And the next lecture, you go to sleep. Okay? All right. I will have pity on you if you fall asleep, but I'll try to make it interesting. All right. So we have 28 lectures, 75 minutes each. So it's a good slog. It's an ultra marathon of sorts, right? So we're just going to plug through, but we're going to cover a lot of territory. Today is a kind of an introductory piece. It's going to be a lot of sprawling in this course, so it'll be a little sprawling today. But I hope you will find some really strong pieces to take off into whatever field that you're sort of central to, right? And I'll make the case, so I'm going to give an introduction, and then we'll have this thing which is a manifesto, right, for complex systems that I have been, I guess, obliged to write or create over time because people keep saying, what are complex systems? All right, so it turns out it's just reality. Okay, so we'll get to that. And I'll give you some of my history so you can know what's been going through my brain for a long time. What is this, 2017? All right, so it's been a long time. Okay, so, all right. I have these slides, which I'm going to work through this one. I'll kind of show you around these slides a little bit as we go. And there's a website that goes with the course, right? So that's an important piece. Maybe I should start with that. I keep sort of evolving these things over time. This will look somewhat like, last year's one. It's when I moved to kind of a different system. So it's all this kind of nice stuff, right? It's adaptive and blah, 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 right? I know it's exciting, but these things look good on the modern day magic rectangles, right? So all of us are just biological agents that carry those things around, right? We're the support systems for the magic rectangles, which have taken over the world. Okay, so, right, we were worried about aliens, but it turns out it's magic rectangles. Okay, things be known. So there's me, that's disappeared on me. There's, I'll tell you a little bit, not too much, but I'll tell you a bit more about me. There are little Easter eggs. The Liberator is for Snow Crash fans. That is just, this is a oblique shout outs thing. You can ignore all those things if they make no sense. But there's little bits that at least keep me amused and sometimes you guys. Okay, you know where you are. We're going to have David Dewhurst, who's a former team member. He's now works with us in the Computational Story Lab as a master's student. He was an undergrad here. So he will be kind of an every person for this course. He'll act as a TA. He'll run some of the office hours. We'll add office hours. He's very excited about it. So he just did them for free last semester, for example. So I can't really control him. He will just do these things. He's actually written up some extra notes to help you guys based on his experience. So just some sort of extra sort of details that might help you navigate through things. This is the 11th season of this. I call these things seasons for some reason. Right, 11 is an excellent number. 17 is a better number, but 11 has some nice properties. So you can read these things later on. I'll talk about these a little bit. Okay, so this is what happens. I record these things maniacally. There's no good reason for this, but I just do it and curate them and put them up online. They're all on YouTube. It's been an interesting thing. I've done this for about 4 years now, and YouTube's changed so much. I mean, YouTube's only 11 years old, which is nuts, right? That's crazy. And to start with, it was just all cat videos. It was pretty hopeless. Bad ones too. Anyway, these things, there are all sorts of good stuff in there. But they go with the slides, and I'm writing a book now as well. We've got a couple of book possibilities coming along. I'll talk about that. We have a special guest executive producer this year because I started a Instagram account for our cat Pratchett, so this is important. Pratchett will appear. He just will appear. If you've been in Matrixology, you'll be familiar with Pratchett. Anyway, so that's true. He did not have an Instagram account. He does now. Yes. So it's what you'd expect. It's many pictures of cats. There's an odd thing with this course of tarot cards. So this is just a little bit of decoration essentially, but these will help as kind of guideposts as we go through, and I'll come back to them as we go through the course, but I'll mention them again later on. This is a ridiculous thing, but eventually these pages will link to all of the material that's relevant to this, right? So this is a whole field in statistical mechanics of percolation, because physicists love coffee, so they name it after coffee, but it's, it's a really lovely thing we'll get to later on. It's about, can you make it from one side to the other if you have some probability of occlusion. That's useful for oil, but it turns out to be useful for, getting oil out of the ground, but it's also useful for understanding contagion and spreading, right, which is a giant story. So these things are all, you can mess around on all these things. Okay, craziness. There's randomness, right? So if you load it again, you get a new one. All right, this is to do with fame, actually, so I'll teach you how to become famous. I'll teach you the mechanism. We can't make it for sure. So yes, 11. I said 11 is a good number. There's an embodiment of 11. There are a couple of things. So there are social places. So YouTube, this eventually will link to a playlist which no one's going to watch, right? I mean, this is just like insane, right? So it's going to be 28 times 75 minutes. That will be what that is. And Twitter, of course, is a big thing for this course. I tweet a lot. That doesn't mean you need to have a Twitter, whatever the verbiage is. I know I should use Snapchat or Instagram or something, but kind of got into the tweets. And so you can just somehow get hold of that, and you don't, however you want to feed that into yourself, there are various ways of accumulating it. Let me show you, let me just finish these pieces, right? So there's Slack here, YouTube, and Twitter. Twitter I'm going to tell you a little bit more about with instructions, so we'll come back to that. So Slack, we'll see how it goes, right? I've used it for a couple of seasons now, and it's really for you guys to talk. It's a polite, good place, right? So you can share things, and David Dewhurst should be on that as well. I won't be on it all the time, but the idea is it's a good place to post things like, I don't understand this, the professor was crazy, blah, blah, blah. Okay, don't say nice things. Okay. Sorry. Let's see. So what's going to happen is, as we go through this took me a while to figure out this was a good idea. There's going to be a huge red button on the front of the website, which will tell you what you're doing right now. Right? That's helpful. So current instructions. So there's your first little blurb. It's just hello, and the tweets are over here, right? So you can come and find tweets here. They will, tweets will announce things like there's a new assignment, there's a new set of slides, whatever it is. They're important pieces. The provost tweeted about this course somewhere. It was totally a fish by my colleague Danforth, but anyway. Okay, sorry. You'll find those things in there. Okay, so instructions. So these will appear, and they'll kind of archive, right? I'll hide them, and they'll just stack up on top of each other as we go through the course. Episodes will appear here, so you'll be able to get hold of them, right? So there's nothing here yet. Slides. Okay, so this has been going for a long time, and I've done ridiculous things with LaTeX and all these other pieces. So there is a whole set of slides up here, right? I'll tweak these as we go along, but I'm fairly happy with the order of things and the content. There's a lot of stuff in these slide sets. It's all built out of LaTeX. There's like 100,000 lines of LaTeX underneath it. And one thing about this course is I am building a book to read with it. That's a different object. I wanted to get an online version first. And when you go into these things, you can link, the references are all there, and you can click on PDFs, right? So you can get the original papers, which, if Elsevier is watching, they'll send me another nasty email. Okay. Publishing is such a ridiculous thing with closed companies. Anyway, so, but there are many, many references that, as I said, link to. If there are books, I'll link to the Amazon page just because that was a thing I could do. And I'm not telling you to buy from there, and I don't get any money from that, right? So that's not what that is, but it's just a way to connect it. We'll touch on very famous papers from, I guess, going back, I mean, some in the 1800s, but 1900s, all the way through, we'll be touching on famous papers from that time, end of the 1900s for networks. So I'll point you to the original stuff, right? So this won't be something that's been pushed through a number of, it's like third or fourth hand. Some of this stuff is very much first hand. So I will be able to tell you about the suffering of science, right, in a direct way, which is important. Okay, so this assignments will appear here. So the first one is going to be here. They will have strange code names. So the first one is called Bizarre Gardening Accident. You can go here. There's going to be one that you can print. There'll be one that's for online viewing, and that has, if it does, it may have things like little YouTube videos embedded in it, right? This will be a PDF and like a little help thing. Let me see. It might not come up very well in this guy. Yeah, so there you go. There's a video appearing in it. It will think about it and it will come back. Okay, right? So that's actually to some part of some slides from last year. You don't have to watch it. It's fine, but it's there. That's the idea. I'm just going to try and connect to the material that we present here, that I present here, so you can always come back to it in an easy way. Okay, yes, so the theme is Spinal Tap for the assignments. That is just for fun. In the past, we've had different themes. So this is, let me see, this one is last year, right? It was, what is this? Princess Bride, which amazingly not so many people of this generation appear to have watched, and that is a tragedy. So I felt that was important, right? Iocane powder is from Australia, of course, where the criminals are. Okay, which is a nice little detail in that scene. I always enjoy that. We can discuss that if you want. Okay, this is from Complex Networks, which is next semester. I'll be teaching Complex Networks. That's every 2 years off. You know, I don't always get to teach it, but it does follow on from PoCS, and it's all about networks, which as we'll see as we go through PoCS, this course, that networks was this huge transition in understanding systems. Yes, so that's a little Monty Python thing. Okay, fine, all right. So that sort of thing happens. So we have some old matrixology fans here, and I just want to show you that I have this course as well, and this was something that I destroyed myself last semester, rebuilding completely. So if you need to learn some linear algebra, there's 72 little videos here, maybe 73, associated with the slides and so on, and yeah, anyway, it's the best. It's the MIT version, Gil Strang. It's totally great. And the last thing I want to show you here, oh, let's see, there's more stuff. Okay, assignments, tarot cards, right? There's a whole thing for them. Great. People want me to make it, so I'm going to publish it as a deck, which is insane. Topics, we'll talk about that today. You know, some stuff here about resources, the things I have to make better, and I'll put up these notes from David Dewhurst that are coming in one of these pieces. I'm going to add some more stuff to data sets here, but these are good things. Let's see, projects. So I have this as a set of slides. That's interesting. This is now a private Twitter account. This is sort of a mad thing. But I thought maybe I could put them up here in some sort of display as possible projects for the course, right? So there are a lot of you here. I hope you all stay. Maybe you won't all stay, but I hope you all stay. But we will end up with enough people to, I think, really have, that we should work in teams, right? So you can work by yourself, but probably good to work in teams. And you know, the way the world is now, most things you work with, you should be probably working with data. You don't have to be, but probably large amounts of data. And I'll probably say this again, but we have some enormous, I'll come back to it, but we have enormous data sets that I will make available to you, and you may be interested. But we have a billion possible projects. Academic outputs, so this isn't working, I gotta fix this up, but there are about at least 40 papers that have been associated with this course in some way, right? Students have been in here, they've done something as a project that has helped build towards a paper. And you know, some of them have been really great successes, so that's a big deal. People have said nice things, so you can look at that, but this is just, makes me feel better because I sometimes look at reviews. I shouldn't do that. Generally people say nice things. So, and I put a lot of time into this, and I get told not to put as much time into it, which is what academics do to each other, right? UVM's pretty good, actually. It's good, you know, like teaching is actually a valued skill here, but it is interesting, and I do this partly because I think everyone should record somehow we should record stuff. You know, we have these great professors in math who are nearing retirement, and they teach beautiful courses, and they'll be gone, you know, there'll be notes, and that won't, it's really a shame. So I've been trying to get that done. Anyway, okay, so that's most things. Pratchett, here you go, you should follow Pratchett. Basically just a source of happiness. We had, let's see if this works, yeah. I painted all this recently. Chipmunk loose in the basement, right? So this was an interesting situation recently. Of course, Pratchett was the one who introduced it into the house, but the chipmunk did the whole I'm dead thing, which was good, and then escaped. So it's 3 or 4 days of a chipmunk in the basement. Anyway, lots of escapades with our friend Pratchett, who is a beloved creature. Anyway, it's really made my life better. It's great. We adopted him. He was 5 years old. I don't know why. I think he was given up because he beat up the other cats in the house. But so now he's happy. It's a one-cat situation. Here he's trying to eat garlic, which he should not do. But this is one of my favorite photos. Okay, great cat, incredible personality. So we can just talk about Pratchett the whole time, but we could also do this. Okay, so what I want to do is get through the overview, and then I'll get to this manifesto thing, which is just a short piece to frame where we are in science, basically. And then we're going to start on scaling, which is a really rich, fantastic field, you know, small to big things. We go from mice to elephants. We go all the way up through life. We go all the way up through technological systems. What kind of patterns appear? It's dead?
No, it's cutting your head off.
Oh, that's disappointing. That's probably not a bad thing, to be honest. What if I do that? Is that better?
Seems to be.
Okay, sad robot. It will, of course, take over the world one day. So I'm going to be nice to it.
They already had, right?
No legs. Yeah, why do they make those cheetah ones? I mean, God, it's very obvious where that's going to go. Okay, better? Okay. High quality recording here. Okay, I'm trying to make it simpler. It's insane. Okay, good. Okay, so we're going to talk about, we have these characters. And now we have Pratchett is the special guest executive producer. So because I can do this, that just will be at the start of every slide set. Okay. I've given you a lot of stuff, I guess, from the website, and I'll skip over things as we need to. But this is going to be just sort of where we're going, basically, and then we'll get to the manifesto. I don't think we need to spend too much, but that's the idea. That's the beginning. So I'll tell you a few other pieces that are associated with everything here. So the complex, we have a Vermont Complex System Center, which has a Robuctopus as a mascot because we have Josh Bongard and we wanted to make him happy. So it's actually a biological octopus in a robot suit, very crazy, but it's just got to have a mascot. So we have a mascot, and it's kind of a fun thing. So this is just a few things that have gone on. It's a group of people that are mostly in math and stats and computer science, but we have affiliations with medicine and people in GUND, for example, in working on earth sciences, and diverse other characters around the university. So lots of funding from different places, people that tagged their work as being complex systems. We've had good press, global press. Different teams have had global press for a long time. And yeah, we had National Geographic recently, which was funny, and Outside Magazine wrote a piece, right, which was, so you should look that one up. That's about Story Lab, Computational Story Lab, which is our team, and it was pretty great. So that was really fun and very unexpected. It was about our work on measuring happiness, so yeah, and health and all that sort of stuff. We've been very much ahead of this big data thing. That goes back into before 2010, I think, when we started to really frame things around this. And we've built these, and I'll have another slide on this, but we have complex systems and data science as sort of our framing here. We've hired people who are actual complex systems people. These are really difficult hires to execute, where you have committees that are distributed from across the university and no one understands anyone, but it's good for them. And the person who comes in gets to choose their department. So this is a very different way of looking at it. You say, we just want people working on some interesting things. Like, it's quite an open time now. I think that's one of the big pieces I want to get across, is sort of a renaissance time in science, right? Things are opening up in all sorts of ways. And there was a sense around 2000 that it was closing down, right? That science was over. But that happens again and again. We'll come to that. We've had good things like career awards. Yes, we have scraps if you're interested in that. That's a Students' Complexity Research and Pizza seminar. Pizza being the important word. But you, as students, get to present their own work, no professors. That's the most important thing. So I started this because it's based on one that I did as an undergrad at MIT, which as a PhD student at MIT, a colleague and I created one called SPAMS, which was the Simple Persons Applied Math seminar, food-based again, but no professors was the important thing. So here are some of those bad people who are part of the team. we're kind of excited to add Laurent, who's coming in the spring from Santa Fe Institute. I'll talk about that. We have some Outpost people. Brian Tivnan, who works with the MITRE Corporation. MITRE does all sorts of things. It's a not-for-profit government. It's not a shadowy one. It's an interesting kind of R&D sort of place. They, for example, do all the like the flight security stuff, for example. They do a lot of that. Okay. And we're working with him, for example, on the financial system. We've got all the data in the financial system, not just the shares that are being sold, but all of the attempts to sell that are made by algorithms and then pulled down, right? So the stuff that's actually invisible. That we've got this data, which is petabytes of data. It's kind of totally crazy. And the gain there is to figure out if the system is vulnerable. There's a flip side of that because DARPA's funding it, which means that they want both sides of that, right? You want to defend and you want to do bad things to other teams. Anyway, so Puck has just joined us as well. So she got the job a year ago, but she's just joined from UCLA. Has kind of a pure math, but also complex systems background. All right, team members. We work on a lot of different things. You can come back to this slide if you want, but really we collectively do work on a lot of different things. And there is a overriding kind of aspect of, well, not completely, but there is an overriding aspect of social phenomena, right? People being involved in all sorts of things, whether it's climate change or whatever it is. There's some aspect of people. So that's become a big thread. And I will talk about socio-technical systems. Like I like thinking that we're in the socio-technocene, people plus computers. Good things that have happened recently, Massmutu. So we've actually a student who was in the very first version of this, which was Basics of Complex Systems, BOX. It was 295 in spring 2007. It's a small group of students. Adam Fox is now the head of data science at Massmutu. And one of our great PhD students has joined that team. So we have it's a $500K pilot investment from them for a year, supporting students and faculty, and actually a data scientist artist person, right? So someone who can make beautiful websites showing all these kind of crazy big data things we've worked on. We also have computer associates involved. They are funding a student and faculty as well. Talking with Johnson & Johnson, which is an enormous company, and it's kind of a hard search problem to figure out where to connect. So there are other pieces that are coming in. But this has been an interesting transition, right? This is in the last few years where data science has really taken off. You've got a lot of people coming in from computer science who are doing machine learning and deep learning and making things work. But I come from a physics background, and it's good to see that people are, actually I come from a social science background. So it's good for two reasons. One is you're starting to see people in industry ask much more about, well, why do these things do these things, right? So somewhere like Massmutu, they're obliged to tell you why they're giving you this insurance. They have to explain it, right? They can't just pop it out of a black box. So black boxes have done very well, but now we're getting to a point where people are really worrying about why they're doing it. So partly there's an explanation thing, but there's also an ethical piece, right? And I'm sure you've seen this, right? So the algorithmic systems are doing things that seem unethical, or, generally speaking, people are pretty unhappy with some of it. Like, so racial biases, for example, are coming through in decisions made by these systems, which can be partly just coded in accidentally, through a very complex kind of way, or it could be because it's derived from people, and people have some issues. But it's very hard to see where that is in those systems, right? So it's kind of a very a nasty sort of emergent property. Okay, I mentioned these that we have. This is the Complex Systems Center. So we have a data science undergrad that's really between math, stats, and computer science. We have these mascots for no great reason, but we do have them. We have a graduate certificate in complex systems. That's 5 courses. This will be complex systems and data science soon. There'll be 3 core courses. This is one of them. Chimbagro's data science 1 will be another. We've got to add it formally. And Maggie Epstein's modeling complex systems. So that's a 5-course piece that anyone in the university can get if they're a graduate student. We have a master's that's running now. So some of you are in that, which is great. Complex systems data science, we're hoping this just grows and grows and grows. And then we're going to have a PhD. So crows are interesting. All right, smart things. But this will be complex systems and data science. We're not yet. this would be much better, but we're not allowed to use those words. Okay, so as I said, these are core courses, Maggie's piece, complex networks is next. I've told you all these things. Yep, master's is here, PhD. All right, so these are just the words. Okay, so that's a little bit about the Vermont Complex System Center. It's been growing again for about the last 10 years. And yeah, good. So we have this team. Many of these people are alums now. They've gone off to all sorts of places. Isabel, for example, was one of our first team members. She went to Cornell to work with some of our very famous colleagues, Strogatz and John Kleinberg in computer science, and now she's in the Facebook data science team, which is pretty small. It's only about 40 people. That's a small, serious team. People are off doing other things. Morgan Frank works with us 2 days a week now, but he's at the Media Lab doing a PhD. So they've done all sorts of great things. You can look at papers on our sites and so on, and I can point you to them later on. But it's been a great 10 years. So I've been working with Chris Danforth during that time, and yeah, so this is a computational story lab. So Chris and I, between us, teach a whole bunch of courses. You're in PoCS now. We have the complex networks is coming up. I mentioned linear algebra, but Chris teaches these good ones here, right? Okay. And as I said, these two, PoCS and complex networks, which for some reason I call coconuts, have produced a whole bunch of papers. So it's kind of I didn't expect that when I came here, but that's become a feature. So that doesn't mean you have to produce a paper by the end of the semester. It's sort of, only get a couple or whatever, it takes years and so on, but that's the idea. And if you're really keen, we can get it done. Okay, this gives you a history of me, just a sort of an excerpt from each paper. But going back, my first paper is 1999, and it's on river networks, right? So this is actually a big data problem back then because these were continental scale data sets, like a mile resolution or a kilometer resolution. And it was about networks, right? Manifest these very beautiful branching networks, which you've seen if you, look at a picture of the Earth or fly over the Earth. And that had an element of a big data problem, and it was kind of shameful almost to work on data. It was interesting. It was an interesting time because the beautiful thing you can do is just have your great idea and then it's true, right? So that still kind of holds a little bit in social sciences. Physicists liked it for a long time. But as we've moved from data scarce to data rich, you can't make stuff up as much as you wanted to. Okay, what that leads into, which we get into the next course, is actually, it's hard to see, but it's blood networks and scaling. So how much energy do organisms use as a function of their size? Very important thing, matters for ecology. There's all sorts of stuff then, and I know I'm just sort of pointing madly at this, about contagion actually, how things spread. So we'll get to that later in the course. Starting around here and here, and actually back here, is work on happiness, which I don't really talk about in this course, but maybe I can show you some things. But we've basically moved into, so there's theory building, there's data analysis, and then there are experiments as well. So for example, this is how to become famous. This is 6 degrees of separation, which we'll talk about, how to connect through social networks, which turns out to be all about social mobilization. It's a very deep problem, very important problem that's had all sorts of legs to it. This gets at how much luck is involved in fame, and it's something we don't figure out because of stories. Stories will be a big part of things as we get further down into this course, and also in my work, we move more and more to stories, including stories in games, right? This is Australian rules football. That was a bit of fun. Okay, but this is Black Lives Matter, for example. This is looked at through Twitter. This is predicting depression and PTSD through Twitter, so lots of other things. Okay. Andy Reagan, I just mentioned him, so he's the one who went off to Massmutu recently. This was his sort of central work for his PhD, was measuring the emotional shapes of books, of stories. So Harry Potter there. I can show you that later. Okay, course information, all these things you will know about, it's fine. I'm just putting them in slides. There's a syllabus, there's a poster, there are other things like that. I mean, I have to make PDFs for people, not for you, for other people. Okay, so a little bit of a guide to how these slides work. let's go find them again. So slides. So you don't have to do this, but if you come back to these, this is the one you want if you're just looking on a computer, right? These are flat slides. It means there are no little slow reveals. It just goes pages through from frame to frame. These ones potentially you can print out, right? So it's got the background removed and there are 6 per page and they're structured like this. Slightly insane. And then these are the ones I present in lectures. So you've just got 3 batches there. All right, that's the idea, okay? You can search around in these things, right? So you can go backwards and forwards with these things. It's got little navigation things. You can search for stuff. If we go to references, say, right, so I mentioned the references before, so this should work. So this should, look at that. Adobe is very scared of everything. That is opened up in some browser that I can't see. Does not allow connection to UVM. That's so weird. Okay, all right, I'll have to fix that in some bizarre security thing. Oh, God. Okay, and we can go backwards. Amazing. Very nervous. Very nervous. Okay. Obvious thing, but web links will look like that, right? Font Awesome is involved. References are at the end. I just showed you that. PDFs are there. If I have a copy, they'll be there. Some books will be linked to on Amazon. Just if you want to know, this is Z-LaTeX is behind this. It's some evolution of Beamer. Somehow there's Perl involved. There's actually Perl inside LaTeX with Perl around it, so it's sort of a turducken of stuff. Anyway, I like these things. But you don't have to worry about that. I like Emacs, and I know that gets people upset. All right, so, okay, Open Sans, so we're working on things. Yeah. I want to put it on GitHub. We'll get to that. That's hard. Yep, episodes. These are bottle episodes because you're trapped. There'll be other tropes. So these are Easter eggs. You don't have to worry about them. Yeah, so the foundational support actually came from a career grant that I had, and it actually came from the social and economic sciences. So that was, it was a nice thing to get that in math. So even though I am in math and stats, but not really. So, okay. This is a shout out to NSF, thank you. Talked about Slack. I will invite you into it. You can tell me maybe in person or whatever, or if you like it or not, if it's useful. I'd like it to be useful. I don't use Blackboard, because I just find it awful, but you can talk to me about that as well. Okay, grading, which I know you, because it is a game, all right? So let's see, assignment's gonna be 60%, 4% for showing up and being good people, 36% for these project talks. And the idea in the past has been an initial talk, so it's like one of these lectures, it's like a little conference. There's a similar sort of thing in the final exam slot, and then a written project as well. What I'd really like is that, and I don't think I have it explicitly written down, is that you set it up on GitHub or something like that if you do a data project, right? And make a visualization that goes with, actually build something that you can show other people. This would be a good product to have. Doesn't have to be like that, but that would be great. Okay. Grading works like this for each question, right? So this is the entire set of grades. You get a 3 out of 3 if it's correct, or there's just one little glitch perhaps. 2, so this is a bit like A, B, C, D, right? So if you don't write anything, you're going to get a 0. 1 for major revision. So this is easy to grade and it's easy to understand. I used to have ridiculous things where a problem would be out of 17 and I'd have to think what that meant, and I didn't know what I meant because I wanted everything to add up to 100. Anyway, so I've adopted this a long time ago and it's good. It's very robust. You know about these things? I'm just putting them up here. So they're there. They're in the syllabus as well, which you can get to on the site. Okay. So topics, right? So this is a graduate course. I know it's a mixture of undergrads and grads, but it is a course that goes between normal kind of coursework courses where it's all been cleaned up and no one knows how anyone figured this out. And it's just like, this is how you do calculus, right? This is just, here are the recipes. To struggling with some real research problems. So we'll get to this manifesto at the end of the lecture, and I have to think about when that happens. Okay. the big theme is that really complex systems is where science is now. We'll talk about these pieces. Some of this will be somewhat philosophical, but limits of things. A big story that winds through all of this is this idea of emergence. It first came out of philosophy, but it's basically the idea that the sum of the parts is different, right, from the whole. Or the whole, say it the other way around. Fool me once. The whole is different from the sum of the parts, and not greater, but different is really the way to think about it. So that's quite a beautiful thing. Universality is this profound piece that comes out of theoretical physics, and it's the idea that the details don't matter, right? So you can change the details of systems and still have the same macro behavior. And so an example that I will come back to even at the end of the course is fluid mechanics, right? So fluid mechanics, we have the Navier-Stokes equations, written down a long, long time ago by very smart people just drawing little boxes with arrows and things and thinking about stuff pushing on each other. And it turns out that some aspects of fluids are very hard to understand, like turbulence and so on, but these are remarkably successful, right? Remarkably successful. And it is talking about a complex system story because molecules of water don't have tornadoes inside them, right? You don't look at a molecule and see, it doesn't tell you tornado, right? Or hurricane or something like that. It doesn't, or cyclone if you're in the other hemisphere. It doesn't say these things. You have to figure that out from how they combine together, right? There isn't a financial collapse in a dollar bill, for example. So, that may seem perhaps trite, but that's a really hard problem to work out, right? So how do you get from these small things interacting in simple ways to giving this macro behavior that's really big and clear and strong? And as you go up through systems, as we sort of evolved in time, I mean, it's remarkable that anything exists, right? That's always, we'll sort of maybe reflect on that, but it hurts. Things have become more and more algorithmic. I mean, biology is much more algorithmic than raw physics, right? We have code. We are very much physical chemical machines as well, but we have code inside us, right? DNA and so on. We have real code. And there's algorithmic behavior in social phenomena and economic phenomena that makes things harder to understand. Okay, but this idea of universality, just to go back to fluids, is that the same equations work for honey as for milk, as for air, as for the earth, which is really remarkable, right? You change the viscosity, you change a little number in these equations, and you'll get the behavior of these other ones. So that's sort of an example of that, but we'll see more profound versions as well. Okay. This is this micro to macro stuff that I was trying to sort of illuminate there with fluid mechanics, right? So that we think about how the little things interact with each other, and then we can end up with a story. In this case, it's partial differential equations, but it's broadly speaking, I'll say a story of how these things evolve in time. A big piece, that's where we're getting to on Thursday for sure, is scaling. This idea of surprise, right? So systems that have, Moore's law is in here, for example. There's all sorts of amazingly cool stuff in here, which is actually ubiquitous. It's not just about semiconductors. Surprise, things like wealth, individual wealth in cities, or how much energy people use in cities. These are all across city sizes, right? There's all these scaling problems. Lots of stuff in biology and mechanical systems. Surprise, right? So things exploding. That's a big issue with complex systems. They go along for a long time and then bad things happen. So how do we kind of understand that in a general way? Networks is an enormous story, right? So, and that was the end of the 90s, and it was because data had become available enough, right? So the web comes into existence in 92, the internet in 69, the web is 92. And then people start to share things, and eventually, you get data sets, and people just start to look at large enough data sets. Right? Computing made all this possible. But that opened up our ability to look at real networks, and for the 50 years before that, really, we just thought about ones that we could imagine in our heads, and they do not exist, actually, which is unfortunate. but they're fun mathematical ones. We'll get to that. Robustness, which is connected to surprise and failure and so on. And the big topic is spreading, how things spread. This is just sort of a big problem that I'll sort of just touch on, but why complexify? Why is there this sort of ratchet of complexification, right? That's something that people have struggled with for a long time now, because there is this law of physics sitting out there that says everything should turn into a soup, right? Which is disappointing, right? But entropy should increase and we should all just diffuse into mud. There's always the long-term promise that we're going to get there. But in the interim, complexification seems to have happened, at least on this little ball that we're sitting on. It's all about stories. Okay. If we explain this, we have a mascot. It's a John Dory. So at least in Australia, you would say, what's the John Dory with something? Which is an aspect of a cryptolect of rhyming slang, which is a Cockney thing. And I guess Australians, being criminals, as you know, had to resort to this sort of language because you're trying to sort of avoid what the powers that be think, right? So, or you want them to not understand what you're talking about. You may have seen these things in like Lock, Stock, and Two Smoking Barrels. There are various movies that have come out of England, for example, where the rhyming slang is rich and complicated, and you can't understand what anyone's saying. But what's the story? It's a very nice, it's like saying, what's up, right? But it's a very nice way of framing that, because it's like, what is the narrative of your existence right now? That's a big debate. Do people live their lives as stories? I don't know, but it's a nice thing. So what's the John Dory? So it's rhyming slang. The best kind of rhyming slang, actually, you drop off the thing that rhymes, and then it's just completely impenetrable. So, and this is an example of it. We even have a word for it. Beers, Edward Lears or Edwards. I will have another Edward, right? Could you get me another Edward from the fridge? Means please beer me, right? Which is ridiculous, but people who are very happy with this, the patter just comes out. Boris Spassky's for Boris's for taxis, right? So just ridiculous things. There are old ones like it's soldiers bold, means it's cold. And then you'll just say, it's soldiers outside, and they're fine. Okay. All right, so, sorry about that, but it's true. You need to know that's what it is. It's a John Dory fish, and it's off of, I think it's sort of New Zealand. They have these. All right, so language is incredibly fun. We'll talk about language a little bit. There's amazingly cool patterns in language. Allometry is this, so it's allometry as opposed to isometry. Aldous Huxley's brother was involved in making that. Julian Huxley was involved in making that a word. We'll touch on that later on. So this is the idea that you get kind of irregular odd scaling, right? Scaling you wouldn't expect. So for example, social phenomena, so if you could say, well, let's double the city size. Let's look at cities over here. We have a whole bunch that have 100,000 people and a whole bunch that have 200,000 people, and look at the crime rates in them, or the disease levels and so on, or how many patents they have per person, for example. And you might think it just doubles, right? That would be sort of a first impression, first guess. But it seems to be that social phenomena have that's good things like creativity, measured say in patents, or wealth, which is sort of a good thing. But bad things like disease and crime, they tend to scale superlinearly, right? So they have a superlinear scaling. Things like actual road surface and stuff that's involved with supplying that city tends to scale sublinearly, right? So that you actually get a returns to scale. So bigger cities are a little more economic in that way. So we'll talk about that. This thing called parallel size distributions. This is an incredibly important thing to know about. That's next week. But this is the idea that many real-world phenomena that we really care about have these so-called heavy-tailed distributions, right? Which connects this idea that you sample from it. This distribution, most of the time you get small things. Now and then you get something large, and then now and something you get much, much larger. And probably the best place that this is kind of codified, because this is a hard thing to understand, people have very bad intuition for this, is actually in floods, but you can see where it's sort of falling apart. But the idea of a 100-year flood or a 1,000-year flood, or 10,000 year flood. That's based on historical data, and it's this idea that these things happen irregularly, right? So there's the every year flood is a boring one. The 10-year flood is something to worry about. The 100-year flood, that's bad. That can cause terrible things. Same with earthquakes, other sorts of natural disasters, right? So we kind of have the right framing in those things, but of course now we have 500-year floods happening like 3 every 10 years or something, right? So you have statistics very hard in these things as well, and people do bad things, like I think I saw a tweet saying, shouldn't look at tweets, saying something about how, look at how we predicted the solar eclipse, right? 85 years ago, people said it would be on the day it was, and this time, and it will be here. Obviously we can predict climate change as well. Like it was sort of this extraordinary reach. It's like, well, these are difficult, that's a big clock, and clocks are pretty good things. The solar system is a nice big clock, and we can predict things very well there. Mercury's orbit, a little tricky because of general relativity, but the climate is harder. Okay, all right, but these things, extremely important to kind of wrap your head around these things, and there's a nice mathematical pattern there. So Gaussians, you will know about Gaussians or normal distributions, right? That's everywhere, and it's a beautiful, fantastic mathematical object, and it does appear everywhere, but they're incredibly boring and you never see them in systems that you care about, right? I mean, you'll see it, but it's not the stuff you're worried about. You're worried about the financial system exploding or, massive floods and so on. Okay, so Zipf's law is to do with, it comes out of language, but we'll see that is used in all sorts of things. A very simple idea, you just take a set of objects, and they have some size associated with them, and rank them from biggest to smallest. And these things tend, again, to have this very skewed distribution. So it could be the number of times a word appears in a book. So for example, is about 4% of words, right? So you just use it over and over again, which seems sort of ridiculous. And about half of the words, half of the lexicon for a book, usually, all those words only appear once. So very skewed kind of thing. But you see this for species, for example, the number of, say, species per genus, or maybe the number of organisms of a species in a forest. There's lots of different examples where this kind of behavior appears. These things are connected. We'll get to them. Talking too much. Okay, so what we want to get to, this is descriptive. We want to get to some of these. And I want to show you these things exist. These are mechanisms for why these distributions come into the world, right? And so the very famous one is a rich gets richer mechanism, right? So that if you're in front, you tend to accrue wealth or whatever the thing is in the system. And it could be just having friends in a network. We'll get to very disappointing things like your friends have more friends than you. That's just true. It's a really disappointing aspect of networks. They have many things that are good more than you, which is awful. I guess people just simply haven't studied the bad pieces. But citations, on average, your colleagues have more citations than you, or more papers, or whatever, right? There's all these sorts of disappointing aspects with networks. But super interesting, and we do not have good intuition for it. I think something that I'll come back to, but maybe I should say now, is we're very good at seeing stories where there's an individual that we can track, right? And many articles are kind of framed in that way. But the things we have to understand about systems are about collectives, and we just don't have the right narrative. The sort of natural narrative architecture that we have doesn't fit it. So we have to learn these mechanisms and kind of discover them, find them, and appreciate them. And try not to tell stories about individuals. Okay, scaling in biology. This is maybe something we won't do, but the scaling piece will start the course off. Okay. Complex networks, as I said, huge thing. It's still going on. Just there's the description of the structure of real world ones. There's how they evolve and change. There are the dynamics on them, right? So spreading on networks that can be coupled with the network itself growing and changing. Just imagine friendship networks or interactions between corporations or supply chains. I mean, there's all sorts of things. And of course, physical networks as well. Right? So there's lots of good stuff in here. There's some very rich kind of mathematical work on random networks, which actually, if you look in the right way, can help you with real world ones. These are I'll spend some time on these because these are pivotal things in sort of kind of exploding the work on complex systems into the 21st century. And these are the names from scale-free networks and small world networks. So this is the Stanley Milgram story, right? The idea that people are not too far away from each other. We'll get into that in detail. It's much bigger than that story. And scale-free networks have these kind of skewed distributions that we talked about as well. They tend to be very prevalent in the world, but no one noticed at all, right? No one noticed. So these are big things. Again, end of the 1900s. Yeah, it's crazy. Okay, lots of other things here. This is a huge thing, is modularity. Like, you've got this huge mess, like maybe hundreds of thousands, millions, tens of millions of interactions between agents. Like, how do you find out if there's actually structure in there? So that's something that people have been working on for a long time. It's sometimes framed as community detection. We might get to that. This is a big deal. So when things fall apart. And so we'll look at some big stories for that. There are a couple of competing ones. This one of so robust yet fragile systems, right? Systems that are there every day until they're not. And it's like it's a big surprise. It goes pop. Right? So the power grid is a great example. And we are continuing to contend with this sort of emergent property of all these little grids that have been connected over time for business reasons and all sorts of other reasons. It wasn't engineered as one big piece, right? So that could have worked out, but it turns out that sometimes you can get a massive failure. India had one a few years ago that I think on the order of 10% of the world's population lost power, which is unbelievable, right? But that's because that becomes possible when you make a big enough system. You get lots of good things, potentially, because you're connecting the system up for some reason that's positive, presumably, but the potential for failure becomes enormous. So the idea of fire breaks, literally for actual fires and then sort of lifted into metaphorically becomes a very important one. So we'll talk about that framing. Okay, highly optimized tolerance will be a really enjoyable piece here. Hot models, great acronym work there. But the idea that you've got things that you've made systems that really do something. They're engineered or evolved to do something really well. But they, in some sort of uncertain environment, but if that environment changes or you're really unlucky, things can go pop. Again, big picture kinds of stories. Connected to this will be, I think in quite a profound way will be, and it seems odd to say, but where you should put Starbucks, right? So it turns out that will be related to that, or hospitals. So you have an uneven population. That's always true in human civilizations, as cities and so on. Where do you put your services? And it depends if you want to make money, like Starbucks, or make people happy or whatever. But you want to make money, or you want to really serve people in a public good kind of way, say as schools or public schools or hospitals. How do you lay those things out? So that turns out to be a kind of a flip or related to this thing. We'll get to that. Okay. Search, that's going to be connected to the small world stuff, but yes, big deals. Okay, so I said spreading is going to be a big piece. So I'll give you a couple of things. It's going to be biological and social spreading, basically. And this is going back into the 60s and then through into the 2000s, models of just very simple kind of ideas of spreading, and then on spreading on networks. Because we always knew networks mattered. It's just that it took a long time to be able to simulate it and solve the right things. Okay, that's fine. I don't need to say these things, but we will get to voting later on, which is interesting. And this will get to how where do superstars come from? Why is the Mona Lisa so famous? Can you make your own Mona Lisa? What do you need to do that? Why is Harry Potter the best book? Incredibly successful book. That's a fun thing, and it's not. We'll just leave that. People get a little confused by that. Okay, so this is kind of how we're going to do it. Complex systems, and I know I'm going to sort of repeat myself a little bit, but I'm trying to frame things. Socio-technical systems will be through it the whole way. We'll go through scaling to start with. Size distributions, it's a power law size distribution. So this is just sort of one slide explaining what we're going to do. We're going to get to mechanisms. So why do we get these kinds of patterns? Robustness of complex systems, networks, big piece, which will be structure, Growth, again, mechanisms. Why do these networks exist, these real-world ones? Turns out the mathematical ones that people thought about for a long time exist because that's what a mathematician would do. They just go pop, but that's not reality, right? There's evolution and growth. And then networks with things acting on them, contagion, voting, and as I said, fame. Okay, and then a little piece at the back end, which is just sort of some thoughts about complexification, right? This is a hard problem, this fight against entropy. But as I want to touch, I just want to say this again and again, but algorithms have become more and more important. There's this, okay, so you can, this will sort of lay out the semester. I think actually, so an important thing will be, I'm going to be away here, and I will give you a makeup lecture of some sort, maybe just record something. But basically this should be the shape of how it lays out. We'll see. Okay, right, good. Okay, so I mentioned the tarot cards. This is just to show you a little bit of history. I thought I was going to make a map and there'll be postcards. But these are real things. There's the normals, so these are the boring mountains. These are Gaussians, unexpected mountains of reality. These will come back. But I just want to show this madness where I've tried to sort of peg things a little bit, right? So these are the very surprising mountains, right? Very boring mountains, but then sometimes they're very tall. So reality is like that. Yeah. So I tried this sort of thing. You don't have to worry about this. I was going to build this whole thing. Obviously, there's some sort of a Princess Bride reference, but then we got to tarot cards. So this is basically the course laid out. This is the sequence we'll go in. All right? Doesn't matter too much, but there are little Easter eggs for you if you like, right? So measurement is a big deal. That's a new one I just added. But there are oblique references to Borges and Indiana Jones. So, okay. All right. Oh, yeah. This is a fun one. Does anyone know what that is? This is about contagion. It's from a TV show. Halloween. It was a Halloween episode, second season. Community. Okay, all right. Really high quality. Okay, just great. And then it went to Yahoo. That's just such a shame. Okay, where things go to die. Projects, as I said, we're going to have teams. Depends on how many of you stay for the madness. As I said, it's going to be sprawling today, and then we'll really work through things that you can work on. The idea is we'll get to a proposal in the first few weeks, and we'll see. I mean, I will have lots of suggestions. We do have, and it's here, right? The VAC, the Vermont Advanced Computing Core, we have a lot of data sets sitting on that. And of course, once you get on it, you can play with them and run all sorts of things. I realize there will be a mixture of coding skills in here. So if we have some teams where we have a balance of people, you want someone who can code, and then you can do some things. We have 10% of all tweets going back to 2008, and we're sort of getting ones from before then, but it's pretty sparse from before then. But that is because we wrote to them. We said, this looks like an interesting thing. It's an amazingly long time ago. And they said, sure, we'll give you 10% of our tweets. And we have a little research feed. And there are only 4 of them working there. It was a tiny little ridiculous thing, which it still is ridiculous, but it's now much bigger. Could vanish, I suppose. But that's a lot of data. It's complicated data. It's interesting data. It's not everything about how people, it's not every utterance every human's ever made. It's nothing like that. But it is kind of a media voice now. It's become more and more, there are more and more bots involved and all sorts of strange dynamics going on with that. So there are lots of things to work on there. I can quickly show you. I know I won't get to that, but this is sort of a centerpiece we have, which is the hedonometer. This is taking all of Twitter, and you can cut it down in different ways. And this is using this happiness measurement thing we have, right? So I'll show you the overall thing. So this is the overall trajectory. This is just sort of an online demo. It's a little hard to explain this in some ways as demographic change, but we'll get there. 2016, we see this kind of downhill piece since then. And I'm just going to tell you what Twitter says collectively. Obviously, lots of diverse voices, but it, so the lowest one was the nightclub in a shooting in Orlando, right? So it was a terrible thing. We have this way of showing you why any text is, sadder or more positive than another. There are lots of sentiment measurement things out there, but if they don't do something like this, and it's just AI. For example, the other day there was a piece in Wired that claimed that Vermont had the highest toxicity rate of trolls, right? Did you see that? Okay, so we got called out a little, like they're saying, well, how do you square that with your thing, right? Because Vermont is actually pretty high in terms of happiness. And we said, well, it's just a different thing. This is from Discuss. They're looking at Discuss comments, and they're using some AI thing to rate comments. And then they're not showing you anything about how that worked. So someone eventually found, a lot of debate on Twitter, and someone eventually found the instrument that you could kind of play with online. There was an online-facing piece. You could put any text in, and it would give you a rating. This is kind of what this, I think, journalist found. I'm not sure what they tried, but they eventually tried and then showed the results from a sequence of these statements, like I am a man, I am a woman, I am a black man, I am a white man. They just had a list of things like this. And the last one was I was a gay black woman, and they went from 10% to 90% in toxicity. Right, so these were just statements of people, fairly flat statements actually of people's identity. So clearly there's something going on. I mean, I mentioned this early on. Algorithms have ethical aspects to them that we're trying to address. So who knows? Who knows what happened with that thing? But Vermont, we think, the tweets come out of Vermont. They're pretty happy. They're muted. The variance isn't as high. Not as much swearing. More stuff about skiing and stuff like that. It does talk a lot about bacon actually, which is interesting. So this has been and I realize I'm sort of torpedoing my attempts to get to the end of the thing, but the last 2 weeks have been remarkable. So whenever there's a negative thing, even like the Pulse nightclub, the next day it's back to pretty much average because people are still talking about that event, but there's just a wash of stories that come back in that push it back up. So deaths of celebrities are often big drops. Robin Williams died, and that was a big drop, and that one kind of persisted for another day a little bit. But we've never really seen anything persist for more than a day. But this, and I'll show you because this is remarkable. This is this is Saturday. And then, this really stayed, right? So it's Sunday, Monday, and then Tuesday. And that's the day, we calculated after the day. That's when, Trump gave that speech that kind of went back on what he'd said. And so this went back down. And then you have the terrorist attack in Barcelona. And now we have Hurricane Harvey. So this has really been a rough couple of weeks in terms of measuring things. And, if you click on this, you can see, right? So here are if you can read that, right? So these are the negative words that are pushing that down, right? Including not, right? Including simply not, right? People were using that piece. We don't do phrases, we don't do context. It's all sorts of things we can talk about. And this is sort of just a front-facing demo thing. Okay. I'm monologuing. Actually, we do not. So actually, those negative days are unexpected. Of course, they're unexpected tragedies. The positive days are they're usually annual holidays. Almost all of them, right? People. Yes, people have bad Thanksgivings, right? They do. And, you'll hear people, right? But Thanksgiving is horrible. Well, that's your personal existence. But thinking about social phenomena, by the way, you should exclude any of your own personal experience because you'll think bad things. Except for sport, right? So sport. So, and there's these sort of examples of, where one team wins, one country beats another country, and we have different languages. So you can see, I think it was Mexico beating Brazil in the Olympics in soccer, and they scored a goal straight away. And you just see Spanish go through the roof with positivity, and Portuguese just drops with all the swearing. It just goes boom, straight down. So you can get, that seems to be the only time where you get collective, sort of instantaneous happiness, but also coupled with tragedy for someone else. Okay. Anyway, what I'm trying to say, that's sort of an example of what we've done with Twitter. We've done a lot of other things, and we don't just work on Twitter. We have actually tens of millions of books, for example. It's a Hathi Trust book thing, so that's an interesting thing if you're interested in that. But we have lots of data on the weather, right? So we have all sorts of different data sets you can play around. Okay, so we're going to try to get through the papers. I've talked about that. And I'll present you with projects, and I might do that in a different way this time. This is something I want you to think about. I mean, I've sort of framed this over a while, narrative hierarchy. There's a little blog post here you can go to. But it's this idea that you really should be able to tell your story at different levels. My wife's a journalist, and in fact, she showed me one day exactly a picture of this that she said, "Oh, this is what you say, right?" And it was exactly this idea. So you should be able to. So graduate students tend to get stuck down here, right? You ask them what they're working on, and then 3 hours later, they've told you about chapter 2. And that's fine, but it really hurts Thanksgiving. But that's, what you need to be able to do is tell, know where you are and how long you've got. And this isn't frivolous, right? These things are really, that's actually deep knowledge, right? If you can get it down to a sentence and really express it well, that's a powerful thing to do. And so these are just little drawings of like, this is the thing that has no substance, right? It's just froth, right? This is maybe a lie or something, a misleading piece. And this is the graduate student, right? They have to be able to put it all together with this idea of a hierarchical thing. So, this is to say that you will be able to present, you'll be asked to present things in different ways, right? 3-minute talks, for example. It depends how many people we have and how many groups, but 30-second talks are sometimes things people do at conferences. They're fun to watch. It's interesting when people do not, get it done. But it's a good challenge, and once you think about the thing the right way. There was a Monty Python thing where I have to summarize Proust, I think. Not get very far. Okay, so let's just mention these pieces, and we'll be good. I don't have to tell you all these things. But I got into this when a friend of mine, this guy here, Andrew Markov, is a brain surgeon. He's back in Australia, handing this book, and he said, "Chaos is done, you should read this," because there was a famous book, James Glick's book, Chaos, which many of us had read at that time, which really got people excited about kind of modern science, right? And it was an extraordinary thing, dynamical systems that were unpredictable. This was a profoundly ridiculous change in, we had quantum, right? That was deeply unsettling, right? Einstein allegedly said God does not play dice. People still, many people still aren't kind of happy about that probabilistic thing. But it turns out later on we got to chaos, and that was this. It's helped us understand, for example, the weather profoundly. We know that we'll never predict more than 2 weeks because of the mixing properties of that system. But complexity, this idea of understanding complex systems, was framed in this book. It was a kind of an attempt to build a book like Glick, who'd had all this fame. And it is inspirational, but it's now a long time ago. And it's about the Santa Fe Institute, right, which was set up by, and I'll just tell you these things, set up by a number of Nobel laureates, including Murray Gell-Mann, who came up with quarks. And so he's a physics Nobel laureate, still around. He must be 90-something now. And a couple of some other physics characters, and a couple of economists, actually, right? So it was a mixed group. Physicists doing the usual physics things, like, oh, we'll solve this for you, it's no problem. This will be easy. There's an XKCD comic for that, of course. But that turned out to be hard, right? And this was also before the big data revolution for a lot of areas of science, right? We'd had it in physics, but in biology was getting there, but social phenomena, not really. I mean, think about astronomy. That's 2000, where you get the big shift, where you start to get arrays of satellites, and the kinds of questions and the kind of skill sets you need are different, become different. But that's only 2000. Anyway, so Markov is a great old friend of mine. There are a couple of books you might want to look at. I'll just mention these. These are the kind of popular ones. It's a friend of ours, Neil Johnson, who's down at the University of Miami, used to be at Oxford. His wife's Colombian, and he's from Essex, and she's like, this is just not a good place to live, so they ended up in Miami. Melanie Mitchell, who's a longtime member of the Santa Fe Institute, and she has online courses that are very much introductory things about complex systems. Has anyone looked at those? Has anyone seen them? Interesting. You know, I think there's sort of like you don't need to know anything stuff, right? But, you know, which is good, although science involves math a little bit. Okay, so, and then Glick, who's great, has this book, and it's from 2011. The information is a very interesting tracing of this kind of growth of data, going back to things like the invention of the alphabet, which is kind of awesome. Super fun, and really is a deluge itself. I had a few other books, I suppose. This is one we'll talk about, Zip, 1949. That's his magnum opus. We'll get to that. That's the Rich Gets Richer story. Philip Ball, who's written so many great things in science, is a science writer. You know, this is a long time ago now, but it's critical mass. This is looking at social phenomena. Schelling, Nobel laureate, very famous character. We'll work on his stuff. These are other pieces. But this is the right framing, evolutionist computation, right? Agent of complexity, that might be of interest to some of you. I like the story thing, so these are a couple of pieces to point you to. These are older ones now. This is from a course at Princeton, but again, it's somewhat older. And you can see it, you know, data wasn't a big piece for this. This is very, you may find my course sprawling. This one is a lot of different things. Okay, Didier Sonnet, very, very smart guy. It's ETH Zurich. But this might be of interest to some of you. Miller and Page are at Michigan, and this is more of a social phenomena thing, so that's, again, something that might be of interest to some of you. For some reason that says their name twice. Okay, Scripps. As I said, Melanie Mitchell, this is the online pieces, you might play around with it. Lada Adamic, who, I want to say Adamic, who's at Facebook with, in the data science team. She left Michigan, has a course online as well, and there's this one, because, yeah. So there are a number of centers around. There's the Santa Fe Institute still around, New England Complex Systems Institute, NEXI, Yanir Bayam. Michigan, which has Mark Newman, I'll talk about his work, who's an incredibly famous, incredibly prolific physicist who's done all this stuff with networks in particular. Northwestern has done a lot of good things. The Kellogg School of Business is a big part of that as well. Lots of places, and then there's us. Okay. A couple of things to point to would be Complexity Digest, which is something you can just kind of feed on. And then Nautilus has done some interesting things over the years in Eon. I mean, people write about this sort of stuff everywhere, but these seem to be very dedicated pieces that are new. Okay, so that's a good place to stop. I'm going to start off next on Thursday with this manifesto, which just frames where we are with science, basically. It says, tries to kind of point out that this complex systems is really a thing. It's not just a bunch of let's have fun stories, very much science, big picture sort of stuff. And then we'll talk about scaling, which is fantastic and diverse and interesting and super, super fun. Okay, so thank you for coming. I hope you come back, and good.